Hello, my name is Ashwarya Pillai. In this video on reduction potentials, you are going to learn how to calculate the Nernst potential of a non-standard cell. Since not all reactions occur at a concentration of 1 molar, a pressure of 1 atmosphere, and a temperature of 25 degrees Celsius, a different method must be utilized to determine the cell potential for a non-standard cell. This can be accomplished by using the Nernst equation. The Nernst equation states that the cell potential is equal to the cell potential at standard conditions minus RT over NF times ln Q, where R and F are constants, T is temperature, and N is the number of moles of electrons transferred, and Q is the reaction quotient. Since T is usually held constant at 25 degrees Celsius, the RT over F term is often simplified to 0.0257. While this equation may seem complicated, it's basically just telling you that non-standard conditions can either increase or decrease the amount of energy the cell can produce, and allowing you to calculate what that new cell potential is. Let's try applying this formula to a question. This question asks you to calculate the cell potential of a galvanic cell given the ionic concentrations and reduction potentials of iron and barium. Since the question stem states that this is a galvanic cell, the reaction must be occurring spontaneously. Thus, iron must be being reduced since its reduction potential is greater than that of barium. So, flip the sign for the reduction potential of barium to get its oxidation potential. Adding up these values gives a standard cell potential of 2.46 volts. Next, calculate the reaction quotient by setting Q equal to the value of the products over the reactants. Remember, though, that since iron and barium are pure solids whose concentrations remain constant, they can be dropped from the equation. Plugging these values into the Nernst equation, in addition to setting N equal to 2, since according to the half reactions 2 electrons are transferred, gives you the following. Plugging into a calculator and solving shows that the new cell under non-standard conditions has a cell potential of 2.43 volts. Try this method again on another question. This one provides you with the entire reaction, meaning that you have to complete the extra step of breaking the reaction down into half reactions and finding their respective reduction potentials from the table. Since, according to the overall reaction, zinc is being oxidized, flip the sign to get an oxidation potential of 0.763 volts. Then, add them together to get a standard cell potential of 1.1 volts. Next, calculate the reaction quotient by setting Q equal to the value of the products over the reactants. Again, remember that since copper and zinc are pure solids whose concentrations remain constant, we can drop them from the equation. Plugging these values into the Nernst equation, in addition to setting N equal to 2, since according to the reaction 2 electrons are transferred, gives you the following. Plugging into a calculator and solving shows that the new cell, under non-standard conditions, has a cell potential of 1.112 volts.